We are 100x away from the theoretical limit of gallium nitride devices.
From EE Tech and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. I won't spoil the story for you today, but this episode has it all. Cloak and dagger executive boardroom moves, little mistakes that turn into big discoveries, and a whole lot of geeking out on semiconductor physics. It's basically my dream episode. I'm joined by Alex Lidow, CEO of EPC, that's Efficient Power Conversion, who is on a mission to replace classic silicon devices with gallium nitride devices. After co-inventing HexFETs at International Rectifier, an invention that made the company about $1 billion in IP royalties, he went on to found EPC. Dr. Alex Lidow, thanks for being here today. I'm excited for this.
Yeah, I am too.
I'm very curious, how early in your life did you realize you were going to end up in the semiconductor industry?
So, I was born into the family. My father and grandfather founded a company before I was born that made power semiconductors as far back as the late 1930s. So it was my life. And I grew up around semiconductors. When I was in high school, my father brought me a junker car and said, make this electric. And I did. Drove that around for a while. And so that was kind of the rail I was on until I got maybe to about junior year in high school. Then I decided I wanted to be an aeronautical engineer. My father was silent about that, but because of that, I went to Caltech because they were the best aeronautical engineering school in the world at the time. And in the first few days, I took a class on solid-state physics, and I fell in love, and I never looked back. So it was short-lived derailing, and then I was on that track for the rest of my life, and very happy about it.
One of the things that really caught my eye when I was going through EE school was the semiconductor physics. It's such a fascinating world, and it's not necessarily counterintuitive, but it's just like its own kind of sub-universe of how the world works that most people don't get to see at all.
It's true. And it is infinitely fascinating. And that's why, here it is, my 50th year in this business, and I'm still fascinated by it.
I would love to hear some family lore, like being inside of kind of the inner workings of the family that founded IR is such a huge opportunity, and I'd love to just kind of hear some maybe early war stories or times that really stand out to you when you kind of understood the impact of what that company did and made.
Look, I mean, the family lore started way back. My father was a Jew going to school in Nazi Germany, 82 to 87. 1932 to 1937. I mean, how risky is that? And he escaped to the United States in late 1937, and after changing truck tires for a year and tinkering and doing this, he took all his money and put an ad in the paper, said, I'm an electrical engineer, somebody want to hire me? And some guy in California said, yeah, I want to hire him. So he got on a bus, went to California. By the time he got there, the guy died.
Oh my goodness.
And so it was terrible, right? So he goes to the house where the widow is and knocks on the door, and she says, yeah, I'm sorry, he died and all this. But I have all this equipment I don't know what to do with. So my father actually moved into the garage and started using the equipment, and that was how he started his first semiconductor company. It was sort of a serendipitous story. And it was a time where the war was just starting, so he benefited quite a bit from the fact that the war needs for modern semiconductors at the time was growing. And then he was able just to keep going and growing and get his father out of post-war Europe after he survived the Holocaust, and that's the environment I grew up in. It was quite extraordinary and taught me a lot about both what to watch out for. What's in your brain is the only thing that you really own, and stories like that that kept me going for a long time.
What an amazing origin story. Tell me a little bit about the development of the HexFET and how you were involved in that and what that looked like.
The HexFET was developed by myself, really, and Tom Herman. Tom Herman and I went to graduate school together, we're buddies. He worked here at EPC until just a few months ago, so we have kind of a life together. But he and I, decided. Well, our first assignment when we went to International Rectifier, that's the company my father and grandfather founded, was to make a better bipolar transistor. Make a better bipolar transistor. So we
Easy, right?
talked about
How
it
hard
for a
could that
while
be?
and said, hey, we just graduated Stanford, knew all about the latest integrated circuits, and maybe we'd apply some of that technology to making a better bipolar transistor. But then, quickly became clear that maybe we should make it a field effect transistor. For those in the audience who know the difference, and we pursued that assignment. A couple of things along the way is we used to make the mask by hand. You'd get a big drafting table and mylar and pens and draw lines and you'd make these things that were like 4x4, and then you'd shrink them down to a tiny little device. And I was doing all the drafting on this at this point, and I made a terrible mistake. I drew a line that was the wrong dimension, and the devices, when we made them at first, they worked poorly. They worked, but they worked poorly. And yet we had already committed to a launch date, and my whole life was at stake here. Because, gosh, I was 24 years old. I mean, this is the end of life if you don't get this right. And it really was because of that mistake that we discovered a really fantastic discovery, which pretty much doubled the efficiency of a device. And then from there, it kind of cascaded. And then we figured out making it cellular was better than making it linear. And over a period of months, just a few months, we came up with 7 basic patents that included the hexagonal structure. It included the structure where there were special wells in there for higher voltage, and you were able to bring them closer together by injecting charge. And all those patents turned out to be quite valuable patents. I think we collected almost $1 billion in royalties from them. But it really was this serendipitous necessity is the mother of invention kind of a story.
What do you think people miss these days by not having the mylar in front of them and the X-Acto knife that they're cutting out?
They miss a lot of cut fingers. A lot of time for meditation, which may be good, may be bad. But by God, I wouldn't go back to it for anything.
Fair enough. We can make different kinds of mistakes now and make different discoveries.
Yeah, it's all true.
My favorite discoveries are ones that are born out of mistakes. And that encourages me so much as someone who makes more mistakes than maybe I'd like to admit. Maybe there's a silver lining there somewhere.
Yeah, covering up your mistakes is a real good way to innovate.
And then you went on to found EPC. Can you talk to me a little bit about what it was like to make that shift? Because I had to imagine at IR, you were kind of, I can use the word golden boy, but you had the last name as part of your resume, right?
Sure. I had the last name. I had a PhD out of Stanford, and developed, basic power MOSFETs, which were the bulk of the revenues. So I was very fortunate to have a platform like International Rectifier to learn all those things and go from R&D into manufacturing, sales, marketing, finally CEO of a publicly traded company with thousands of employees. I was golden boy. And that's about when I got fired. In my early 50s, there was a couple of directors, a board of directors that decided that they knew how to run the company better. It was long enough as a family affair, and get the old guys out. So my father, me before him, but I was fired unceremoniously, and he was deposed as chairman. Then you have to rethink what you're doing. It was a very big surprise to me. It was very rapid and very shocking.
I have to imagine it was quite the shock. How soon did you start to see it as an opportunity versus a setback?
So my firing occurred on October 2nd, and I had about 1 day's notice that it would occur. And I was, and it would occur at a board meeting that would occur in later that day. So I was standing in the shower thinking about what the heck I should do. I'd spent at that point 30 years of my career working on energy efficiency. I felt that was really critical for our planet, for a lot of reasons. It improved our standard of living, it had potential for improving the way we treat our environment, and postpone things like global warming and acidification of the ocean. So I thought, man, I want to still stay in that thing. And you know what the best thing to do there would be is to have a carbon exchange, to open up a carbon exchange where people can trade carbon credits and all this kind of thing. Or alternatively, I could look back at my 30-year history and my graduate work in compound semiconductors, and maybe I could do something there, because it looks like gallium nitride is a pretty promising material. And so in the shower, I weighed those two, and I said, well, maybe I better do gallium nitride, and that was it. And that later that day, I started working on a business plan and never looked back at that either. But it did teach me, it was a smarter decision to use my experience rather than maybe something else.
How do you separate recognizing a fad from like an actual technical industry trend? So gallium nitride, early days, is kind of interesting, but not necessarily well developed. How do you decide, yes, this is something we want to go after?
So, gallium nitride was in many ways, it was similar to gallium arsenide. I did my PhD work in the mid-'70s in gallium arsenide. And the first thing I did when I graduated was I went to silicon, because I thought gallium arsenide will never happen. Well, it did happen, but it didn't happen in the way I thought. And for the reasons that I understood, the difficulty of processing it, the expense of growing the crystal, and the limitations of the device in certain very key areas. So rather than discarding all the knowledge that I gained as a graduate student, I filed it in the back of my brain. And as silicon hit the theoretical limits at the end of the millennium, I recognized that there was some work done in Japan to grow gallium nitride on a standard piece of silicon. And it was device grade. And that really triggered a lot of thinking. First of all, gallium nitride is more robust than gallium arsenide, so it solves some of the problems. You can make a very robust semiconductor out of it, and growing it on silicon solved the problem of having to grow a very expensive crystal. So in 2002, I started an effort at International Rectifier to work on gallium nitride devices. And it was going kind of slow because it was very primitive. You had to, basically make your own epi reactors and invent everything from scratch. And I was CEO, big company, had a lot of distractions. So when I got fired, the distractions went away. And I decided that, learning all those lessons, gallium nitride still had a very good chance of being a broadly applicable semiconductor, but there were certain problems that hadn't been solved. And of course, as a startup, you have very little to lose, a lot to gain. I had no money. I didn't have a golden parachute or anything like that. So it was necessity was the mother of invention there, and we got going pretty quickly.
So you mentioned gallium nitride being grown on top of silicon. So are you starting with the wafer? I imagine there's not like a big ingot of gallium nitride that's happening.
Correct.
What does that look like?
So you start with a silicon wafer. Now, when you make a MOSFET, or almost all the semiconductor made on silicon, they actually grow an epitaxial layer of silicon on top of it. Okay, and that's you put it in a reactor and it blows gases over it and it grows a crystal. Now with gallium nitride, same thing. You put it in a reactor and you can't quite grow gallium nitride because it doesn't match the lattice of silicon. So what you do is you stick it in there and you grow aluminum nitride, and then you grow aluminum gallium nitride, and then you grow a little less aluminum, and then it's gallium nitride. And okay. So it was not an easy thing to do, but the folks in Japan figured that out, and I was standing on the shoulder of giants for that one, for sure.
So then I imagine once you have that wafer with your gallium nitride grown on top of it, you can do your more standard silicon processes with it, like
Absolutely.
implementation and etching and all that.
That was the
Okay.
beauty of gallium nitride, is it has properties of chemical properties like high melting temperature and decomposition temperature. So it was more like silicon. Gallium arsenide would decompose at very low temperature. So you could actually run it in a standard silicon furnace, or standard silicon techniques could be used for it. So, as I was standing there on the street with my cardboard box uh, without a job, I thought, well, gosh, I could get going with gallium nitride by just using a standard foundry. If I could just find a standard silicon foundry that would be willing to accept the risk of having a contaminant like gallium nitride in their fab. And I went to a few of them, and I found one called Episode Technologies, where the owner and founder I had done business with before. He was a very visionary guy, Archie Wang, and he said, "Sure, let's try it." And he let me try it in his fab. And again, this cost almost nothing to try it, and it was appeared to be successful pretty early on. We invented some remarkable stuff that was all compatible with silicon processing, and that was a key to a low investment strategy startup.
Interesting. Yeah, I love the idea of kind of you on the corner with your briefcase, an idea looking for someone that will take a shot on you, very similar to your grandpa. I love to nerd out on the physics of this stuff. Can you talk to me a little bit about like the Bliga curve and how silicon versus GaN works out in terms of like electron mobility and dielectric strength, that sort of thing?
Yeah, gallium nitride has a couple of remarkable properties. First of all, almost everything stems from two properties. One is strong chemical bond. Silicon, gallium and nitrogen bond in a tighter bond, a higher energy bond than silicon. So that makes it a wide band gap. Wide band gap means how much energy it takes to pull an electron off, and that's related to how strong that bond is. So wide band gap, that's great. And then the second property, explain why these are important. The second property is the polar molecule. The crystal gallium nitride that commonly grows on silicon is polar. And what that means is if you bend it, it generates an electric field. That's what polar is. So with those two things, all sorts of miraculous stuff happens. First of all, by having a tight chemical bond, it takes a very high electric field to break the bond and pull off electrons. What that means is you can withstand a lot of voltage over a very small distance. So for a power device, you can locate terminals much closer together so the electrons don't have very far to go. And therefore, the resistance between those two terminals is going to be a lot less than it would be in silicon. Good news, because power devices really count on the resistance between the two terminals, usually a source and a drain. And so the second miraculous thing is that because of this polar molecule, if you can squeeze the top of the crystal that bends all those crystals, you can generate a huge electric field which attracts electrons to the surface, like that. When you squeeze it, make a little thin layer of aluminum gallium nitride, which has a different lattice constant, squeezes the heck out of the gallium nitride, and sucks all these electrons up to the surface so hard that they actually get compressed into an electron cloud, which is quantum mechanical. And when that happens, you get much higher mobility. The electrons scoot along as a sort of one probability function as opposed to a bunch of little probability functions. And so the mobility starts going very high, much higher than silicon, much higher than silicon carbide. And so now you have the two factors that your terminals are close together and your electrons have very little internal resistance. So you can make these miraculous devices, 1,000 times better than silicon power devices. And that's of course very alluring. And if you can overcome some of the difficulties in growing the crystal, we had to invent a way of making it enhancement mode instead of depletion mode. And then you've got to figure out how to work out all the kinks that might cause reliability problems as well.
Can you talk to me about enhanced mode versus depletion mode?
So the enhancement mode device is off unless you apply a voltage on the gate. And that's a good thing, because if you've got electricity and a lot of power available to you, you don't want to have to, generate some sort of electrical field to turn it off. A depletion mode device, it is normally on. It will be a short circuit until you figure out a way of getting enough voltage on that gate terminal to turn it off. So very early on, this had not been done. When we started EPC, we said, this is the challenge we need to overcome to make this generally acceptable. We need to invent a way of making it normally off, or enhancement mode, and we did.
This is relatively new in the last 15 years. Like 2009, I think, is when you came out with the enhancement mode tech. There's still, I think, a lot of misconceptions around gallium nitride devices. Can you talk through what do engineers often struggle to understand until they've done a little bit more research?
Yeah. So one of the things is, I use an analogy. If you spent, your first 40 years of your career driving a stick shift Volkswagen Beetle, and then somebody handed you a Ferrari, gave you the keys, and said, drive it as fast as you can, you'd probably run off the side of the road pretty quick. And gallium nitride is extraordinarily high performance compared to silicon. So the first problem that we encountered was that people who had been used to designing with MOSFETs didn't know how to handle these very high dVdTs and dIdTs. And so designs tend to be flawed the first time, the second time, the third time. And some people would get discouraged. So very early on, we realized that we had to invest an awful lot in education, an awful lot in having technical people that could actually work with the customers directly, which is expensive. It's slow. But I think we worked through that. And so, once you work through that, then you've got the next misconception. Gallium nitride's too expensive. You've got to work through that. Gallium nitride's not as reliable as silicon. You have to work through that. And I think now we've pretty much proved all of those old myths to be false.
Yeah, I remember maybe 2012, 2013, I was just starting out, and someone said, hey, our customer wants this probe, and the specs were like hundreds of volts and hundreds of megahertz. And it was like, what in the world are these people doing that they need that kind of insight into their design? It turns out it was GaN.
Yeah.
What are some of the maybe most fun reactions or most surprising reactions you've had as people started to discover this technology?
Look, I think that there are some people who just realized that it was the thing that made their business happen. And the first one that we saw, and that was Dave Hall. He was the founder of Velodyne. And Dave came to us very, very early on, right after we introduced our parts, and said, I think that gallium nitride might be the key to something I'm working on called LiDAR. That's light detection and ranging. He said, because, LiDAR using silicon just doesn't have the resolution, and so it can't compete with radar. I didn't even know what he was talking about. But he said that with GaN, I can go fast enough that I can compete with radar, and I can make some marvelous things. And it turns out that in light detection ranging, you're shooting a packet of photons and measuring how long it takes for them to bounce back to a detector. And in that way, you can measure time of flight, gives you distance. And if you spin it around on a disk, you can see all around you 360 degrees, which is what he was inventing. And that spinning LiDAR became the origin of the early and even today's autonomous vehicles. He was heavily motivated to learn how to use GaN right away and did it very well. So when somebody was very heavily motivated, we knew they could succeed. And so all you had to do was find more motivated people to make the rest of the world understand what GaN could do.
What other spaces do you see GaN being used heavily? I know my fast chargers are usually GaN devices, but I know there's more out than that. Can you share some examples?
Yeah, I think that, when I did the early MOSFETs, when we did the early MOSFETs, we replaced bipolar transistors, and there was a dynamic. Why is it taking so long? What does it take? All this kind of thing. And it really occurred tipping point by tipping point. You found an application that really needed that, and then it would tip over, and then that became the default. With MOSFETs, the first default was the AC to DC silver box that went inside desktop computers, and that just made the volumes high enough that the cost came down, and the next tipping point was actually plotters, and the next tipping point was anti-lock brakes, and it went on like that until it was so cheap and so everybody knew how to use it, so that's what everybody used. And now today, very few bipolar transistors. With GaN, LiDAR was the first tipping point. It was the first thing that generated enough volume for us to really get kind of fluid and fluent in making it. And then the second tipping point that hit was space electronics. What we knew and were able to demonstrate was gallium nitride could be made so it wasn't susceptible to radiation effects. And silicon devices are very sensitive to radiation. So we were able to then show that you could make stuff that you didn't need shielding for, that could withstand, all sorts of terrible radiation without any ill effects. And so satellite manufacturers kind of got over their risk aversion and started using it pretty early on, and it became a healthy market. I would say the third tipping point that happened was GaN fast chargers. No thanks to me, by the way, or EPC. That was done by Navitas. And a team that actually I'd hired right out of college when I was at International Rectifier. Very smart people, Gene Sheridan, Dan Kinzer, and a host of folks that I've known their whole adult lives. And they decided that GaN would make very good in a fast charger. They would be able to squeeze the size of the charger down so that something that used to be a 5 watt blister charger now could do 65 watts. And that, of course, became a big hit. They went public. It became very popular. And then the next tipping point was all these AI systems. They need very high density power supplies. And sure enough, the best way to do that's GaN. It was our GaN. And so sure enough, every single one of these power supplies, or every single one of these AI systems, has a little tiny power supply that looks like this on it. Sometimes they have more of them. It's a 1,000-watt power supply. And all those shiny
1,000 watts?
Yeah, 1,000 watts. It sits right there next to that GPU, going blazing fast and doing crazy things. If I turn it around, there's more on the other side. So there's a lot of GaN devices, and AI is obviously on a hype cycle of some sort, but it's doing very well. And so all that's built up the momentum. Now, in the meantime, GaN's gotten less and less expensive. It's maybe 5 or 6 years now since we were actually able to price our GaN lower than silicon. So it's now in a snowballing thing. This last few tipping points have really tipped it over where it's a generally accepted solution to a lot of problems.
1,000 watts in that package. I'm still a little hung up on the thermal management. Must be a whole new ballgame for GaN devices then.
Well, so thermal management is tricky, but the best way to manage thermals is don't generate them. So that's the thing about GaN. Those little electrons are pretty slippery, so they don't generate a lot of heat. And something like I was just showing you there, that can be 98% efficient. So at 1,000 watts now, you're generating 20 watts of power loss, and it's not hard to dissipate 20 watts in something this big. But if it were, say, 96% and it was 40 watts, it wouldn't be possible.
You mentioned getting GaN devices cheaper than silicon. How important was it in early days to be kind of a pin for pin, footprint for footprint match?
Well, I'd say that in early days, we realized that was unadvisable because the MOSFETs were, because they're slower devices, they were extremely inefficiently packaged. And if you put a Ferrari engine into a Volkswagen, you still have a Volkswagen. And that's what we were dealing with. So what we had to do was we had to basically strip away the package so that you had the naked performance of the device available to you. And that's why we went with wafer level chip scale in the early days. Now, of course, we have packaged devices, but they're very different than MOSFET packages.
Okay. No, that makes sense. I'm trying to picture a little Beetle just getting ripped apart by a Ferrari engine.
with some Italian guy with driving gloves, right?
Right. How was the yield in the early days, and was there any weird sort of things you had to do to improve that, or was it pretty much on par with silicon?
Well, so in the early days, we're making stuff and nothing's working. We're making more stuff and nothing's working. But it was kind of one of those whack-a-mole jobs where this part would work and then that other characteristic was bad, and then you'd make that one good and the other characteristic went bad, and we were playing whack-a-mole, whack-a-mole, whack-a-mole. And then in January 2009. We had a small team, and one of the members of our team, Alana Nakata, who I'd worked with again since she was right out of school in the 80s at the International Rectifier. And she was just one of the most diligent people in the world. And she just would look at these wafers and she would test every single device. I mean, there are thousands of them there, every single device by hand to make sure that this was working. And she found one device that worked, that had all the characteristics at the same time. I remember it was January 2009. And, we'd made by that time probably 1 million devices. She found the one that worked. And when you have an existence proof, it gives you a whole nother level of confidence that you can make this happen. And so based on that, we really just had renewed confidence this is possible, and we just dissected that device and what was it and what we did, and we made it, and the next time we had more of them, and then we had more of them, and eventually we got to the point where our yields are pretty much matching silicon yields.
Kind of a needle in a haystack situation of like, we think it's possible. Let's add some variability and just find the one that works. Is that kind of how it went?
We didn't intentionally add variability. It just happened.
Yeah, that's part of the process for sure. For sure. We'll be back in just a moment, but this episode is sponsored by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from thousands of leading brands. Come discover, design, develop. And now, back to Dr. Alex Lidow, CEO of EPC. If you could go back and tell yourself something 15 years ago, not necessarily like a technical spec, but a mentality or an approach, what would you tell yourself?
Wow. So going back 15 years, that's the very first days of us building product that worked, right? 15 years ago, January, that's 15 years. I'm not sure what the lessons were. I mean, I'd say that every person I know that started a company that was successful, and I think ours is successful now, so I can get into that camp, said the same thing. They said, if I had known what I would have to go through, I never would have done it. And I think that's true. It is terrifying to not just start a company, but start a company on an inventive notion, and not knowing what the invention is, and having to do something that is going to require more and more funds, and not having those funds. So you have to figure out where to get them. Those are terrifying. I'm not sure it's a good lesson, but if you're faint of heart, don't do it, because it is, and to this day, it's still a 24/7 mental grind. And if you enjoy it, as I do, it's pretty stimulating.
Yeah, so almost on some level you'd tell yourself to not do it, but here we are.
Yeah, or just realize that you're going to go through some hell and you're going to have some joy. So you better learn how to enjoy the joy and how to absorb the pain. And there's a lot of both.
Celebrate the wins, roll with the punches.
There you go. Better way of saying it.
Let's move future looking a little bit. It seems to me like the potential of GaN is we're just barely scratching the surface of this. Where do you see this technology going over the next, 1 year, 5 year, 50 year? When
we started our first generation gallium nitride devices, were better than silicon. Better than silicon's theoretical capability as well. So we knew we had something that was useful, because silicon could reach into that. But since then, we've improved the devices about 10x over 15 years. We are 100x away from the theoretical limit of GaN. So I think that the technology has a lot to deliver on in the next few years. There is a vital technology. It will keep improving. And even better than that, we can integrate stuff on our GaN devices that are hard to integrate in silicon. So we're making devices like monolithic power stages that you really can't do in a monolithic silicon device very well at all. And that, I think, is also a core element of the future. These monolithic power stages that's how power conversion is done in power stages. And so, all of that's going to be integrated. There won't be a discrete device out there. As a matter of fact, I believe that in the next couple of years, we won't make any more discrete devices. They'll all be ICs of some form or another. And I think that's a huge boost in productivity and performance as well as cost that's coming forward. Shrink the die, add functionality, and wow, never look back at silicon.
Could you break down some examples for me of here's some discrete devices that you sell today? You've been kind of your bread and butter for the last 10 years. And what sort of device do you expect to be making in 10 years from now as a concept?
So as a very basic element, a transistor, is a gate, a drain, and a source. Those are the three things in a field effect transistor. It always gets hooked up in a certain way in a circuit. 80% of all the circuits are a half bridge. So you got a high side transistor, you got a low side transistor, and then you've got drivers and you've got level shifters and a few common functions. So the first thing is we'll integrate all that, especially if it gives you performance advantage, which it does for a variety of reasons. And that's our power stage products. And then you've got to figure out how to get that cost to be much lower than the discrete devices, which we've done. And so you get the performance, you get the cost. Of course, it makes things smaller as well. So you get the size advantage. And that's where you want to go. Now, why aren't all devices like that? Well, because the minute you do that, you sort of narrow down your market. A discrete device can be used in a power supply, it can be used in a motor drive, it can be used in a LiDAR system, it can be that. The minute you start sticking in these complex circuits, it is focused on an application. It becomes application specific. So you need to have those applications that are large enough to drive the integration as an improvement. And so we're seeing more and more of those. We're seeing it in LiDAR. We're adding a driver plus a simple driver plus a transistor makes the LiDAR much higher performance, and it didn't add any cost. We're seeing it in motor drives, where making these power stages, you put 3 of those power stages together and a controller, and now you have a brushless DC motor. Well, that's a whole lot simpler than doing it with a bunch of MOSFETs. I mean, you're saving 80% of the componentry. And when you're doing something like a drone that flies in the sky, you don't want a lot of stuff. You want to have things as light and small as possible. So there's just an example where these kinds of integration add huge value. In space, same thing. Our ICs are really in high demand for space applications because of the space and efficiency savings.
Yeah, I didn't realize GaN was kind of naturally rad hard. Is there anything specific about its physical makeup that makes it less susceptible to that?
So parts of it are natural and parts of it are unnatural. So the natural part is gallium nitride field effect transistors, HEMTs. There was a high electron mobility transistor. They don't have an oxide gate. In silicon, you have an oxide that is your MOS, it's the O. And that oxide traps charge. Particularly, it traps like gamma radiation or electron charges. And that charge causes the threshold voltage to go down, down, down. And finally, it goes negative, and then your device is a depletion mode device that blows up. So we don't have that problem. So that takes care of light radiation, gamma radiation, which is the highest sensitivity of silicon. Then there's 2 other forms of radiation. One is neutrons and protons, a little heavier than electrons. They also have a charge. So they have that problem, but they also, since they have mass, they will bang into a crystal, and eventually you bang enough, you start cracking the crystal. And so that's called displacement damage. Now, because of the tighter bond between gallium and nitrogen, it's harder to create displacement damage. So you have an advantage that's 100x right there, more than 100x on neutrons. But then you have heavy ions. And these are the things that are really energetic. They're flying out of the sun near the speed of light, and they have the weight of like gold or things like that. I mean, they're really heavy. And they will just blast your crystal. But they also carry with them enough electric charge that they can create a lightning strike inside your device. So blasting the crystal with momentum is, again, displacement damage. GaN has an advantage there. GaN also has an advantage in that there's really no efficient minority carrier conduction, which means that when you have a energetic particle going through your device at a huge speed, it doesn't generate a whole electron cloud, which it happens that it does in silicon. When you create that cloud of carriers, what it is a momentary short circuit. And, power devices, power system guys don't like momentary short circuits. That's just bad news. So they have to do all sorts of stuff to compensate for that. And you don't have that in GaN. You do have the issue of having to manage those very high electric fields that occur during those strikes. And that is a tricky design and material issue, which we've overcome. So there's some very special engineering you have to do that's special to a rad-hard device. So they're not the same as our commercial devices. But GaN starts off with a basic advantage.
I never thought about geometries playing into rad-hard devices. I always just thought slap some more shielding on it. But
yeah, well, you got terminals in GaN in particular. You have terminals with very high electric fields, right? Much higher than in silicon because the terminals are closer together. That makes it pretty sporty when a very energetic particle goes in there.
So as we look forward, obviously space is going to be a huge industry for semiconductors. What other areas do you see that GaN could be improved on? And are there any lines of research going on now that get you particularly excited?
Well, so are you talking about applications? Because there's some exciting applications coming up.
Let's do it. Yeah, applications sounds good.
Yeah, no, I mean, I'm just really very excited in something that a year ago I wrote off as being nonsense. But now I realize it's not. And, a lot of that has to do with GaN, actually. And that's humanoid robots. Humanoid robots, they'll go up a hype cycle and all that kind of stuff. But we're at an early stage where they're beginning to be functional. And the economics of a humanoid robot for very basic repetitive functions like warehousing, cooking fast food, making cappuccinos, the economics are starting to work out. So I think that with our aging population and the low birth rates, we're going to have a chronic problem of labor shortage, particularly for undesirable jobs. And humanoid robots, if manufactured in volumes like automobiles, will certainly cost less than automobiles and will certainly, on an hourly basis, be the lowest cost way of doing those functions. And that's exciting. Now, it's exciting also because GaN has a big role in there. A humanoid robot has about 40 motors on it to make everything crank. And I told you about those ICs. Those ICs are ideal for those fingers, toes, ankles, knees, and hips and neck and all that. And so we're seeing, even in a low volume build of humanoid robots, there's a very high GaN content for the motor drives. But it doesn't stop there. Humanoid robot needs eyes. What are the eyes? Well, put a LiDAR system there. Because one LiDAR system gives you, 3D awareness right away, and that's good. What do you need for a brain? AI system. What's powering all the AI systems? Well, that's GaN. And there's a variety of other functions, battery chargers, DC distribution inside. All of that is GaN because it's smaller, lighter weight, more efficient, higher power. And so it's kind of, when you have a white piece of paper and no preconceived notions, you default to GaN. And the humanoid robot is the best example. And I think it'll be a very important one for our society going forward. Not without negative consequences, of course, but probably offsetting positive consequences.
You're the second person this week I've heard talk about themselves being excited about humanoid robots and seeing a future there, because I also have, kind of like that's a fanciful like sci-fi, like put on a show sort of concept, but to hear two very smart people in the course of a week say that, it has me second guessing my original impressions.
Well, mine too. I wrote it off as a stunt. Something that gets a lot of clicks. But now I've studied it quite a bit, and I see that we're still not there, but there is a future, and I want to be in on the ground floor.
Speaking of ground floor and people getting started with GaN, you have written the textbook on GaN called the GaN transistors for efficient power conversion. And you have a new version coming out in just a couple months.
We have lots of books.
Can you tell us a little bit about, why write a textbook? Because that is a massive undertaking.
I mentioned earlier about training being something we identified very early on as being critical. Also, we realized that the earlier you get an engineer, the more likely they are to buy your GaN when they graduate. So we thought that we would also invest in, university level training. And the best way to do that is through textbooks, of course, working with professors as well. So we partnered up with Wiley, John Wiley, the publisher, does a lot of these textbooks. They're peer reviewed, and we came out, I guess it's now 10 years ago with the earliest edition. And then, there's a second edition and a third edition. Those are all out. And since it's a fast moving technology, Wiley's been doing this every 5 years. And so now we've just finished up. It's in final review, the fourth edition, and that'll be out in December. And it has just a bunch of stuff that wasn't available 5 years ago in it. The complete reliability models, thermal models, the latest in integrated circuitry, the latest in space electronics, the latest in very high density DC to DC, the latest in motor drives that wasn't there 5 years ago. So this technology moves quickly, so we need to be constantly refreshing the texts that our students are using.
I feel like I could talk to you all day, but we like to do some lightning round questions at the end, some quick questions, quick answers. My first question for you, if you could wave a magic wand and change a law of physics or fix an architecture, make it work, what sort of magical change would you make to the universe?
I would get rid of interface traps. I know most people would say that. It's a very common question. I get it all the time.
Okay.
But those are the things that really get you. In silicon, contamination and control of line widths is the key to making a better silicon device. In gallium nitride, it's stress, strain, and traps. So you had to learn a whole different physics. And I wish I didn't have to, but it did.
In your time developing semiconductors, what has been the most surprising or unusual application that you've come across?
Whoa, surprising application for GaN. We were surprised by LiDAR because I didn't know what the heck that was. And I was really surprised because it made it a viable thing. And look at how big LiDAR is now. It's on every autonomous car. It's probably on every one of those robotic vacuum cleaners that you might have running around at night in your home. It's ubiquitous now. And that really blew my mind, and in a good way.
It's amazing how cheaply you can pick up a little LiDAR. I have one sitting around here. It's just like a little LiDAR module is like dozens of dollars now. It's really accessible as a technology.
Well, if you look at some, really cheap ones, they're sub $1 because it's just firing an LED and seeing what comes back. Sure. That's what those vacuum cleaner robots do.
For people who are looking to adopt more GaN or learn more about it, other than your book, how do you recommend people get started in implementing and building themselves like a mental framework for implementing GaN into their devices?
I think that there's some very good tools out there. If you go on our website, you'll see a GaN first time right, thing, and it basically walks you through it. The 8 stages of a development of a product. First you figure out what you want to do, and each one of them has resources underneath it that helps walk you through it with GaN. How to select the right device, how to design it so that you don't have you don't have a lot of ringing, how to design it thermally, how to measure it once you've got it. Because, like you said, with the probes, if you measure these things with old probes, you're not going to measure anything because they're too fast. Those are, and there are a lot of resources. There's hundreds of webinars that are available, all of them online. And I would certainly start with GaN First Time Right on our website to get you going, and it'll work.
All right. Check out EPC's website.
epc-co.com.
Wonderful. Well, thank you so much for your time today. This has been a fascinating conversation.
It's been a delight. Thanks so much.
That was Dr. Alex Lidow, CEO of EPC, and what a great time. Thanks for joining me today in the lobby. If you liked this episode, please share it with someone that you think will like it too. Word of mouth is the #1 way podcasts grow, so it really does help us when you share these episodes. Also, thank you to Mouser for sponsoring this podcast. And come check out the Moore's Lobby social pages, and you can see a video clip of the large semi-truck sitting behind Alex in his office and hear what that semi-truck symbolizes. It's worth heading to LinkedIn to see that clip. Again, thanks for tuning in. I'm Daniel Bogdanoff, and I'll catch you next time.